Okay, so after abruptly cutting that last one off, I'm going to do the solution for 23 here. I just did that because I realized I had about 20 minutes, and I don't like to go over 20 minutes too much because it takes about an hour for me to upload a 20-minute video. And I realized I had a bit to go here. So let's take a look at B. 23B says, what is the temperature of 0.257 moles of O2 occupying 6.78 liters at 0.856 atmospheres? So, we're going to use PV equals nRT. Lydia. Shh. It's a big book crawling around. Yes, Lydia, that's great. Okay, we are trying to find temperature. So we're going to solve for T. We're going to divide each side by N over R. So PV divided by N over R. So temperature equals PV over NR. Just double checking because I am awful tired right now. And my pencil is not working, and I cannot find any more pencils. Oh, there's a pencil. And I have tons of them around here somewhere. So temperature, that is what we're after. N, I'm getting a value of 0.257 moles. V equals 6.78 liters. P is 0.856 atmospheres. So R, because I'm in atmospheres and liters, is going to be 0.0821. There. So let's go ahead and plug these numbers in. So temperature, 0.856. Atmospheres, volume, 6.78 liters, divided by 0.257 moles times R, which is 0.0821. So temperature, when I multiply the top numbers and divide those by the bottom numbers multiplied together, is 275K. And I should have canceled out my units for you too to show me doing that, so I'll go back and do that. This ends up being 1 over K, so that's why, excuse me, the K goes to the top. Okay, 23C. C says, what is the pressure of 25.6 grams of Cl2 occupying 15.6 liters at 28.6 degrees Celsius? One thing I want to say is, you know that you have to use the ideal gas law when you're only given one set of conditions. You use Boyle's law and Gay-Lussac's and all of that when you have two sets of conditions. You have two pressures, you have two volumes, you have two temperatures, okay? This is when you only have one set of conditions. So, again, PV equals nRT. They want to know pressure. So, divide each side by V. I get PV over V equals nRT over V. So P equals nRT over V. I'm looking for pressure. For N, they don't give me the number of moles, they give me the mass, but I have 25.6 grams of chlorine gas, and I know how to find the moles. That is 2 times the molar mass of chlorine, which is 35.45 grams of chlorine, which is 1 mole of chlorine gas. So divide 25.6 by 2 times 35, which is about 70-ish, and you get 0.361 moles of chlorine gas. Okay, so we have N. Temperature is 28.6 degrees Celsius plus 273, which is 301.6 Kelvin. Volume is 15.6 liters. So my R value that I'm going to choose is the one with atmospheres, because if I have a choice, that's what I use. So plugging into my equation, P equals, my number of moles is 0.361. My R value temperature and divide all of that by volume. When I multiply those together, divide by 15.6, I get 0.573 atmospheres. 3 significant digits because I have 3 here and 3 here and 3 there. Okay. So moving on to 24, this is a stoichiometry problem. I apologize I didn't give this to you earlier when we did the stoichiometry, but the way the book had it set up, they told me a different section for this that we would need, so that's why I didn't give it to you earlier. So this is 24. Now for 24, I am going to write the equation at the top because we really need that equation. 4C3H5N3O9 yields 6N2 plus 12CO2 plus 10 H2O plus O2. So for 24A, we are told when nitroglycerin explodes, nitrogen, carbon dioxide, water, and oxygen gases are released initially. Assume that the gases from the explosion cool to standard conditions without reacting further. So A, if 16.7 moles of nitroglycerin react, how many liters of N2 are produced? So we have 16.7 moles of nitroglycerin. Now I'm already in moles, so I can go right to my molar ratio. And so if I look here, 4 moles of nitroglycerin will react to produce, I'm after nitrogen, 6 moles of nitrogen. But I want to know the volume. but I know at STP that 1 mole of nitrogen is 22.4 liters of nitrogen. So all of my units cancel out, and I get 561 liters of nitrogen. When I multiply across the top and divide by 4. For B, this is a little bit more involved here. I need the molar mass for this one, and so I want to make this hopefully a little nicer looking for you, especially if you couldn't follow what I did on my other paper. So the molar mass, remember, 3 times 12.01 grams. This is from your periodic table, finding those molar masses. We learned how to do that last chapter. Oh, I'm not writing those very well. When we multiply and add all of that up, we get 227.1 grams of nitroglycerin is 1 mole. Okay, so going down here, I'm going to start way over here so that maybe I can actually get all of this in. So we start with our known number, our 1 kilogram of nitroglycerin. The problem is we have to be in grams. So we know that 1 kilogram of nitroglycerin is 1,000 grams. So that cancels out. We need to get to moles. So we have grams. We figured out our molar mass up above, so we know that 227.1 grams of nitroglycerin is 1 mole of nitroglycerin. From here, now the question says, this is a little tricky here, what is the total volume of gas at STP produced when 1 kilogram of nitroglycerin reacts? Well, up here, 4 moles of nitroglycerin produces a total of 6 plus 12, which is 18, plus 10, which is 28, plus 1, which is 29 moles of gas. And each one of those moles of gas is 22.4 liters of gas. Because remember, it doesn't matter what the gas is. They all have the same molar volume at STP. So when I multiply these numbers across the top and divide them by the numbers that are on the bottom, I get 561. Nope, sorry. That was the other problem. 715 liters of gas. That is a lot of gas. Okay, that is a lot of gas. All right, going on to 25. Actually, I'm going to write the equation. And for this one, I'm actually going to copy over the states of matter because I'm going to comment on this. If I remember to. Okay. So for A, says a reaction between ammonia and oxygen is the first step in the preparation of nitric acid, HNO3, on a commercial scale. The reactants are mixed at STP. The products are produced at 1000 degrees Celsius and at atmospheric pressure. So we're given this equation. So A, what volume of NO is produced in the reaction vessel by the reaction of half a mole of oxygen? So I can figure this out at STP by doing this conversion. So half a mole of oxygen is, I'm in moles, so I want to go to NO. So oxygen has a 5 in front. 5 moles of oxygen yields 4 moles of NO. 1 mole of NO is 22.4 liters. When I go ahead and do the multiplication, divide by 5, I get 8.96 liters of NO. But this is at STP. The gases are going to be at 1000 degrees Celsius. So I go ahead and I do V1 over T1 equals V2 over T2. My initial volume is my 8.96 liters. My temperature is 273 K because I'm at STP. I want to know my volume at 1000 degrees Celsius, which they give me is 1273 Kelvin. So I plug into my equation. 8.96 liters over 273 K is V2 over 1273 K. Multiply both sides by my 1273. Cancel out my units. Cancel there. V2 equals, when I multiply these numbers, divide by 273, 41.8 liters. Okay, so that's 25A. 25B. The question says, what mass of water is produced by the reaction of 15 liters of NH3 at STP? So, for this one, as far as the water is concerned, because it's not volume and it's not a gas, it's a liquid that's produced, we don't have to do anything with the gas laws. This is just a straight stoichiometry problem. So, 15 liters of NH3, and that is a STP. So we know that at STP 15 liters is 22.4 liters of NH3 is 1 mole. We look at our equation and there's a 4 in front of the NH3, so that's 4 moles of NH3 produces 6 moles of water. There's a 6 in front of the water. And I get that right from my equation here, 4 and 6. I'm trying to find mass. So I know that 1 mole of water, oh, I need to know the molar mass. So I come down here, 2 times 1.008, I get this from my periodic table, plus 16.00 is 18.016 grams. So 18.016 grams of water. These all cancel out, making sure that my tops cancel out my bottoms. And I get 18.1 grams of water. Okay, and finally C, yay, we're almost done. How many liters of oxygen must react to produce 33.5 liters of NO? So this is kind of the opposite of the first problem. So we go here and we say V1 over T1 equals V2 over T2. V1, T1. So V1 is 33.5 liters. Now the NO is on the right side of the equation, which is at 1,000 degrees Celsius. So its temperature is 1273 K. I want to know its volume at STP because that's what the oxygen is at, which is 273 K. So I plug in my values, 33.5 over 1273, V2 over 273. Multiply both sides by 273. V2 equals 7.18 liters of NO. This would be at STP. Now, I can use my stoichiometry to convert to oxygen. So I have 7.18 liters of NO. I know that 22.4 liters is 1 mole. So now I'm in moles. I can get to oxygen now because I know from my equation, where did my equation go? Right here. 4 moles of NO is produced by 5 moles of oxygen. 4 from 5. I'm now in oxygen and I want liters of oxygen. So 1 mole of oxygen is 22.4 liters of oxygen. So moles cancel. Now the other thing that cancels nicely is this 22.4. I could have kind of skipped that step, but I don't like to do that because I like to make sure that I don't leave anything out. So multiply across the top, divide by 4, and I get 8.98 liters of oxygen. So that is it for the chapter. I will be putting up some lab videos, and I will hopefully see you on Zoom on Friday.